What's up, guys? It's Tala here again, and today we are going to do some practical work instead of just reading the theory of the slides. So here I have got the slides of our lecture, that is matrices, and we are going to cover whatever we can in this short video about matrices, and how they relate and how do we work with them inside MATLAB. So let's get started. So first of all, an m cross n, so this asterisk is actually the multiplication, the cross symbol, when we use it manually. So an m cross n matrix is a two-dimensional array of numbers consisting of m rows and n columns. Special cases are a column vector where n equals 1 and m equals 0, and a row vector where m equals 1 and columns equals 0. So they are called column vector and row vector. So no, actually, sorry, special cases are column vector where n equals 1. So where n equals 1 and means the column, the number of columns is 1 and the number of rows can be any number, and same is with row vector where m equals 1 and number of columns can be any number. So I'm sorry, I said 0. It isn't actually 0, it can be any number, because if it's 0 it cannot happen, because if row is 1, column will have to be 1 or greater. So that's the thing. Matrices are fundamental to MATLAB, and even if you're not intending to use MATLAB for linear algebra computations, you will have to become familiar with matrix generation and manipulation. So even if you're not using MATLAB, you should at least know what the matrices are, because you are going to have to work with this concept in math, linear algebra, and inside many other fields as well. So you need to become familiar with this. So let's start. Matrices. A matrix array is two-dimensional, having both multiple rows and multiple columns, similar to vector arrays. So it's kind of a vector arrays where you can have multiple rows or multiple columns. So it begins with the left angled uh, square bracket and ends with the right angled square bracket, sorry. Spaces or commas are used to separate elements within a row. So within a row, for example, this one, they are used to say they are spaces or commas. Spaces are used to separate these elements, and semicolons are enter key is pressed to separate rows. So here, if we're going to write it in MATLAB, we're going to put a semicolon here that will separate the number of rows. So, and this is an m cross n matrix, so it has m rows and n columns. So, and this is the main diagonal of this matrix. So for example, as I said, 1 2 3, we use spaces to separate the elements within a row, and then the semicolon to separate rows, and then we have 4 5 6, and we are separating the number of elements inside this row. So here matrices can be built explicitly using the square bracket notation. So you can explicitly build a matrix using this method, or you can use this method as well. So both will do the same job. And for example, the 3 by 3 matrix comprising of 9 prime numbers. So these are the 9 prime numbers which are used in this matrix, and this matrix has been made with the matrix general notation. The end of a row can be specified by a semicolon instead of carriage return. So a more compact command with the same effect is semicolon separated rows. So just like this, within a row, elements can be separated by spaces or by commas or by separate columns. So here, what I'm going to do is I'm going to create a matrix A and equals, let's say I do 1 2 3 and okay, 4 5. Okay, it's not working. I see. Okay, so let's see how do you do that. Actually, I haven't practiced this, so I'm still curious how do you do that. So if you set up with the command, the end of a row can be specified by semicolon instead of carriage return. So, but how do you, because when I press enter, it is, so here 1 2 3, and when I press enter it, okay, so 4 5 6 and 7 8 9, and let's see. Oh, okay, so it will go to the start of the page, so it won't start from here, from the same line. It will start on the next line and from the start of the next line. So I was confused in that. So either you can write it like this, or what you can do is you can create a matrix 1 2 3, and you can use a semicolon, and then you can write 4 5 6, and then a semicolon, and then 7 8 9. You always got to remember to add spaces, and there you go. As you can see, both have the same result. So you can do either ways, but this looks kind of messy, and this looks kind of it's not that much readable, except this one is much more readable than this one. So I would prefer, uh, I personally would prefer this one over this one. So but that's a personal choice. Okay, so matrix addressing. So matrix name, row, column may be used in place of a row or a column reference to select the entire row or column. So here, for example, here if I want to address this 5, for example, so I'll have to write A, then the row. So 5 is in the second row, that's right, and then 5 is in the first and second column, so 2 2, and it will give me answer 5. But what if I want to address this whole column 2 5 8? So what I would do is, so I want to address whole column, so what I will do is um, yeah, so in every row I want to address the second element. So in every row, this row, this and this one, I want to address the second elements of every row. So 1 2 3, and that will come, that is, all these elements comprise of the second column of this matrix, so it will give me the second column. So okay, unexpected MATLAB expression, why is that? Let me just check. Okay, so you also have to include a comma. I'm sorry. So as I said, this is my first time too that I'm practicing this, so you gotta have to bear with it. So, and there you go. It is giving you the second column because it's addressing every element of every row, every second element of every row. So that's why it's giving you the whole second column. Now let's go to the next one. So here this is matrices continued, more commands, identity matrix. So first the transpose, so B equals A transpose. So if I here, so what transpose is, it converts your columns into rows and rows into columns. And if after performing the transpose operation on a matrix, if it remains the same, you call it symmetrical matrix. And if only the signs change, means plus change into minus or minus change into plus, you call it asymmetric. So let's say B equals A transpose, and as you can see, the columns change into rows and rows change into columns. So that is what transpose is all about. Identity matrix IN returns an n into an identity matrix IMN returns an m cross n matrix with ones on the main diagonal and zeros elsewhere. So here, let's say, let me clear this first of all. Let's say I want to have a n cross n 2 by 2 matrix, an identity matrix, an identity square matrix of size 2 by 2. So there you go. And if I want to explicitly specify the number of rows and columns, so for example 2 rows and 4 columns, so it will give me this, because the main diagonal is this one, and it doesn't go any further, so it is 1 1. And if I go like I not 0, let's say 1 2, and as you can see it says 1 rows 2 columns, but the main diagonal has the only element 1 here. So that's about the identity matrix. Addition and subtraction, that's pretty easy. If you add two, for example, if I add C equals A plus B, it adds in each individual entries of each matrix with the corresponding entries. Same goes with subtraction. Scalar multiplication, so for example if I multiply 0, so 0 0 into C will be all zeros. Matrix multiplication, so that's the basic the multiplication which is according to the rules and principles of linear algebra, and for that to happen the number of columns in the first matrix should be equal to the number of rows in the second matrix. And as A and B are both square matrices, so we don't have to worry about the conditions. So A into B, and as you can see this is how they multiplied the matrices, and this is what we got. Then we have matrix inverse, so inverse of A, this is a function. A must be a square matrix in this case, because for an inverse to exist we gotta have to first find the determinant, and if a matrix isn't a square matrix, its determinant cannot be found, and then you have to find the adjacent of a matrix, then you have to 1 over determinant into adjoint of the matrix, and that gives you the inverse of a matrix. And a rank, and the rank of A returns the rank of matrix A, so means after the transformation of a matrix or a vector, how much has its dimensions changed. So that is what the ranks gives you. So for example, if I so transpose of, let's say, C, so inverse of C, and matrix is close to singular or badly scaled, results may be inaccurate. Okay, so singular means that the determinant was equal to 0 and its inverse does not exist, so it's telling me that it was close to singular. Alright, let's say inverse of A, and it still gives me this. Let's say inverse of B, matrix is singular. Okay, so its inverse does not exist. I see. So singular matrices with the determinant cannot exist. We all know that. Then we have rank. So if you guys want to check the rank of B, it gives you 2 because it has 2 dimensions. And if the dimensions were decreased or after the transformation, it will also give you that. So but here it's a square matrix, that is why it has two dimensions. And here matrix powers, if you do dot power, it will square each element. And if you do A cross A or A times A, computes A into A, and A must be a square matrix. It's because if A is not a square matrix, then the possibility is much higher that the number of columns in the first matrix is not equal to the number of rows in the second one. And I think it's always the case where that happens. So it should be a square matrix, and the determinant can be easily calculated by, so here's a perfect example. If we calculate the determinant of B, it should give us 0 because the inverse did not exist, as we saw. As you can see, determinant of B is 0. Let's compute determinant of C, because it was telling us was pretty close to 0. And as you can see, it is indeed pretty close to 0, maybe power minus 13. Let's say inverse of A, and determinant of A, and it's still minus 16. So these both are very close to 0, but determinant of B is exactly 0. So B is a singular matrix. So I think, guys, it's pretty much it for today's video, because this video has been really long and I can feel it actually. So the next video I'll start from this slide, inshallah, and onwards. I'll see you guys then. Till then, goodbye and take care.